All right, so today we're diving deep into deep learning
Deep learning, yeah.
with excerpts from the book Deep Learning
Oh, yeah, the Goodfellow book.
by Ian Goodfellow and Yoshua Bengio and Aaron Corville.
It's really the Bible in this field.
And we're going to be going chapter by chapter
Oh, wow.
to give everyone a comprehensive breakdown of
Oh,
everything.
that's fun.
So consider this like your crash course through deep learning.
Hopefully without the crash.
Without the crashing and burning.
Yeah.
Yeah, just pure knowledge gains.
That's what we like.
So are you ready?
Absolutely.
Okay, so chapter 1 kicks off by asking, what even is deep learning?
It's a great question to start with.
Because it's a lot more than just like neural networks, right?
Yeah, it's definitely deeper than that.
Ooh.
Pun intended.
Okay, so then what is it?
Well, in essence, deep learning is about computers learning multiple layers of representation from data.
Multiple layers.
Like imagine a computer trying to recognize a cat in a picture.
Okay.
Instead of just looking for simple shapes like circles and triangles. Yeah.
A deep learning model breaks down the problem into layers.
Okay.
So first it might detect edges and textures.
Right.
Then it combines those into simple shapes. Then those shapes into ears, tails, and so on.
Okay.
Until it finally recognizes, hey, that's a cat.
Ah.
And this layered approach can be applied in various frameworks, not just those inspired by the brain.
So it's kind of like a detective piecing together clues
Yeah,
from tiny details to the complete picture.
I like that analogy.
And then the book also mentions this really fascinating history of AI,
Yes.
where research and funding would go through these periods of boom and bust.
They call them AI winters.
AI winters.
Yeah, when the enthusiasm, the funding kind of dries up.
Because people aren't seeing the results, I guess,
Right.
they're expecting.
Exactly.
And it's fascinating how certain terms, like cybernetics and connectionism,
Oh, yeah.
kind of faded in and out of popularity.
Yeah, but the core ideas behind deep learning, they kind of persisted
Like they were waiting.
to come back.
Yeah. Exactly. Leading to the resurgence we're seeing today.
It's pretty cool.
Yeah, I think it speaks to the power of these ideas that they survive those periods of disillusionment.
Yeah, like a seed that's dormant for years,
Yeah,
waiting for the right conditions.
exactly.
So before we go full on deep learning, though,
Yeah,
the book kind of lays the groundwork with machine learning.
right, which is still super relevant.
Yeah, machine learning is already having a huge impact on our lives.
Oh, absolutely. It's everywhere, even if we don't realize it.
Totally.
Like those spam filters that save our inboxes from overflowing with junk.
Yes, definitely.
That's machine learning in action.
It is.
Or consider how some hospitals use machine learning to help doctors make really critical decisions.
Oh, wow.
Like recommending a C-section in high-risk pregnancies.
That's really interesting.
These systems are trained on huge amounts of data to learn patterns and make predictions.
Without being explicitly programmed.
Exactly.
That's kind of mind-blowing that computers can learn these complex tasks just by analyzing data.
It is amazing.
Speaking of data, though,
Right.
Chapter 2 delves into the math behind it all. And I gotta be honest, it's not for the faint of heart.
It can be a little intimidating,
Yeah.
but the book doesn't shy away from the technical side,
No.
but it presents the math in a way that's very accessible,
That's good.
even if you're a little rusty.
Like me.
So linear algebra is a big one.
Okay.
Concepts like transpose, dot product, inverse matrices, these are all essential.
Oh my gosh, college flashbacks.
Yeah, right?
I remember those.
But they're important because they describe how deep learning models process information.
So it's like learning the grammar
Right.
of how these models communicate.
I like that.
And then there's probability and information theory.
Yes, those are crucial for understanding uncertainty
Uncertainty.
and making predictions from data.
Okay.
So concepts like probability distributions.
Like the bell curve?
Exactly. Bell curve we all know and love.
Yeah.
Ideas like covariance and entropy. These help us quantify how much information is contained in data
Right.
and how confident our models can be in their predictions.
So it's like giving these models a way to reason about the world, not just blindly crunch numbers.
That's a good way to put it.
And then Chapter 3 gets into the core of machine learning itself
Okay, the basics.
before diving into the deep end.
All right.
So what are the different types of machine learning?
Well, there are three main types.
Okay.
Supervised learning, unsupervised learning, and reinforcement learning.
Okay, so supervised learning.
Yeah, that's like having a teacher guiding you,
Okay.
giving you labeled data and saying, this is a cat, this is a dog.
Like showing flashcards.
Exactly.
Okay, what about unsupervised learning?
That's more like exploring a new city without a map.
Interesting.
You're trying to discover patterns and structure in unlabeled data.
Okay, so no one's telling you,
Right.
what anything is, you have to figure it out.
Exactly. You have to figure it out yourself.
Cool. And reinforcement learning.
Reinforcement learning is like training a puppy.
Oh.
You reward good behavior and discourage bad behavior.
Interesting.
And the model learns through trial and error.
I love these analogies.
Yeah, they're helpful.
It's like giving these learning algorithms different personalities.
Well, I like it.
And learning styles.
Definitely.
But how do we know if a model is actually learning?
That's a great question.
And not just memorizing the answers.
Yeah.
Like a student who just crams for a test.
Exactly. That's where generalization comes in.
Generalization.
How a model performs on data it's never seen before.
Oh, like,
that's the real test.
so it can't just memorize.
You're right.
It has to be able to apply
Exactly.
what it's learned.
And a big challenge is avoiding overfitting.
Overfitting.
Where a model performs great on the training data, but bombs on new data.
Like that student who memorizes the textbook but can't actually apply the concepts.
Exactly.
I've definitely been that student.
We all have at some point.
So to combat overfitting, we use techniques like regularization.
Yes.
Which are kind of like training wheels for our model.
I like that analogy.
They prevent it from getting too specific to the training data.
Exactly.
And help it learn more general patterns.
It's like teaching a student to understand the concepts, not just memorize the answers.
Exact.
It's much more valuable in the long run.
So in Chapter 4, we finally start building those neural networks.
Lego time.
Lego time.
We love Legos.
I know.
So imagine building with Legos.
Okay.
We stack layers of interconnected neurons that process information.
Neurons.
Yeah, kind of like the building blocks of the brain.
But artificial neurons?
Yes, artificial neurons.
The
simplest type is a feed-forward network.
Feed-forward network.
Where information flows in one direction from input to output.
Like a chain of dominoes.
Exactly, a chain of dominoes falling.
And to make these networks more powerful, we use activation functions.
Ah, yes. Activation functions.
Which introduce nonlinearity.
They're essential.
They allow the network to learn complex curve relationships in the data.
So instead of just drawing straight lines, these activation functions let the network draw squiggly lines.
Ooh, squiggly lines.
And capture all those intricate patterns.
That makes a lot of sense.
And then there's backpropagation.
Backpropagation.
The algorithm that makes the magic happen during training.
Okay.
It's like a feedback loop that tells the network how to adjust its weights.
To get better at its task.
Exactly. Imagine a chef tasting a dish and then tweaking the recipe.
Okay.
That's kind of what backpropagation does.
Constantly refining the model.
Right.
Like a sculptor chipping away at a block of marble.
Until the masterpiece emerges.
I like that analogy.
But even with these powerful tools, we still need to be careful about overfitting.
Right, back to overfitting.
It's a constant battle.
And that's where Chapter 5 comes in.
Okay.
Diving deep into regularization for deep learning.
We've got a whole arsenal of techniques here.
Bring on the arsenal.
I like your enthusiasm.
I'm ready.
So one common approach is parameter norm penalties.
Parameter norm penalties.
These add a penalty to the cost function based on the size of the weights.
Okay.
Discouraging the model from having excessively large weights.
Gotcha.
Which can lead to overfitting.
Okay, so it's kind of like adding a tax on complexity.
That's a good way to think about it.
The model has to pay a price.
Right.
For having too many intricate connections.
So it encourages the model to be more economical.
Yeah.
Finding simpler explanations whenever possible.
What are some other techniques in this arsenal?
Well, there's dataset augmentation.
Dataset augmentation.
Which is like giving the model more training data.
Okay.
But with a twist.
A twist.
We create modified versions of existing examples by rotating, flipping, or cropping images, for instance.
Okay, so you're showing the model different perspectives on the same data.
This exposes the model to variations of the data and helps it learn more robust features.
It's like showing a child different pictures of a cat.
Yeah.
Sitting, standing, sleeping.
Right.
So they can learn to recognize a cat.
Exactly.
In any position.
Very good.
What else?
Then there's dropout.
Dropout.
A technique that randomly turns off some neurons during training.
Turns off neurons.
Yeah, we randomly silence some of them.
Interesting.
This forces the network to learn redundant representations.
Okay.
And become less reliant on any single neuron.
So it's like a team where everyone has to be able to step up and cover for each other.
That's a great analogy.
Okay, cool. What else?
Then we have early stopping.
Early stopping.
Which is like taking a cake out of the oven before it burns.
Ooh, I like that one.
We monitor the model's performance on a separate data set
Okay.
and stop training when the performance starts to decrease.
So you're preventing it from overfitting.
Exactly. We're finding that sweet spot where the model has learned enough
Okay.
without getting too
So
specialized.
it's like Goldilocks and the Three Bears.
Yep.
Not too hot, not too cold.
Just right.
That's right.
And finally, there's adversarial training,
Adversarial training.
a fascinating technique where we pit the model against an adversary.
Adversary.
Yeah, that tries to fool it with carefully crafted examples.
Wow.
This forces the model to become more robust.
So it's like training with a really tough opponent
Exactly.
to make sure you're ready for anything.
It's like giving the model a sparring partner
Yeah.
to help it hone its defenses
That's a cool way to think about it.
and become a more skilled fighter.
So this arsenal of regularization techniques is pretty impressive.
It's quite a toolbox.
It really shows how much thought and creativity goes into addressing the challenge of overfitting.
Absolutely. It's one of the biggest challenges in depth learning.
But training these intricate networks isn't exactly a walk in the park, is it?
You're right. Optimizing deep learning models is a whole other beast.
Which we'll talk about next time.
Yeah.
But for now, I think we've covered a lot of ground. We've gone from understanding the core concepts of deep learning to building neural networks
Yeah.
and even learning how to keep them from getting too cocky
Right.
with regularization.
It's amazing how much complexity and ingenuity is packed into this field.
It really is.
What are your thoughts so far?
I'm really struck by the parallels between how deep learning models learn
Yeah,
and how humans learn.
that's a great observation.
The different learning styles, the importance of generalization, the need to avoid overfitting. It's also relatable.
It is.
It makes me wonder if understanding how these models learn
Yeah.
can also give us insights into how our own brains work.
That's a fascinating thought.
Like, can we learn about ourselves by studying
Right.
these artificial systems?
It's something that researchers are actively exploring.
That's so cool.
Yeah, the connections between deep learning and neuroscience are becoming increasingly intriguing.
Can't wait to see what they uncover.
Me too.
I'm also really curious to learn more about these optimization algorithms.
Oh, yeah.
How do they actually find the best solutions for these complex models?
Well, that's what we're going to delve into next time.
Right.
We'll uncover the secrets of deep learning optimization.
Awesome. Can't wait.
Should be fun. Welcome back to our deep dive into deep learning. Last time we left off with this whole idea of regularization and how to keep our models in check. But now are you ready to really go into how these models learn?
Yeah, like we've built this amazing machine, but now we need to figure out how to like fine-tune it
Right, exactly.
to perform at its best. I'm ready for the secrets of deep learning optimization.
Okay, well, chapter 6 is where the fun really begins.
Right.
This chapter dives into the world of optimization algorithms, the engines that power the learning process.
Okay, so it's not just enough to have the model. We have to have a way to
Right.
train it.
We need a way to find the best settings for all those parameters.
Right.
And that's where optimization comes in.
So what are some of the challenges in optimizing these deep neural networks?
Well, one major challenge is that the loss function, the thing we're trying to minimize, it can be really complex. It's often non-convex, meaning it can have lots of valleys or local minima.
So we could get stuck in a valley that's not the lowest point overall
Exactly.
and miss out on a better solution.
That's the risk. And deep neural networks, with their millions of parameters, they can have loss surfaces that look more like a wild, rugged mountain range than a smooth, predictable hill.
Oh, wow. So it's not just about climbing the highest mountain.
No.
It's about finding the right mountain to climb.
Right. You don't want to climb a tiny, isolated peak that gives you a misleading view.
And what about those saddle points?
Yes, saddle points, those are tricky too. They're like plateaus on a mountain.
Yeah.
You're not going uphill or downhill, but you're not at the peak either.
So you could be fooled into thinking you've reached the summit
Exactly, and then you're stuck.
when you're really miles away from the true peak.
Right, they can trap our algorithms into thinking they've found a solution when they're really just stuck in a flat, featureless region.
And I imagine with these complex landscapes, there are probably other obstacles too.
Oh yeah, definitely. Like cliffs and exploding gradients, these can happen when the gradient becomes very large, causing the optimization process to become unstable.
So it's like taking a steep, unexpected drop while hiking.
Exactly.
Suddenly you're tumbling down the mountain.
Instead of making steady progress.
So it sounds like optimizing deep neural networks requires a special set of skills and tools.
It does, and the book provides those tools in the form of these specialized algorithms.
Okay, bring on the algorithms.
One workhorse is stochastic gradient descent, or SGD.
SGD.
It's a simple but effective approach that updates the model's parameters in the direction of the negative gradient.
Okay, so it's basically taking small steps downhill,
Right.
guided by the slope of the lost surface.
Like a careful hiker making their way down a mountain.
But what about those plateaus and valleys that can trip us up?
Well, that's where techniques like momentum come in.
Momentum.
Momentum helps the algorithm